So, good afternoon, everyone. Welcome to Pacific Salmon Commission Seminar Series on Environmental Variation in Pacific Salmon Management, the view from both sides of the border. My name's John Holmes. You've seen me do this several times, and I'm the Canadian co-chair of the Coho Technical Committee. And I'm pleased to introduce the 17th seminar in our monthly series titled, and this particular seminar is titled Fisheries Management Structures to Address Climate Change, featuring Dr. Tommy Moore from the Northwest Indian Fisheries Commissions, who will be speaking on climate change and fisheries in the Pacific Northwest, current and future conditions, and Dr. Rishi Sharma from the FAO speaking on dynamic reference points in the context of climate change. So our seminar today is on management structures and climate change. Many of you will know and have heard Gary Morishima, who can't be here today, but has consistently made the point during discussions on climate change at PSC events that if we're going to foster resilience to climate change, then it's not enough to simply understand how the species and stocks that we care about respond to climate change. We also need to look at the systems and processes used to assess and manage them and ensure that those systems and processes are adaptable and resilient to climate change as well. That is, we need to understand as scientists and managers how we can be adaptable and resilient in what we are doing for the resource. So today's seminar is one small step in the transition to climate-aware management and assessment systems with speakers who bring local and global perspectives to the debate. We need to incorporate new ways of delivering the science needed for our changing environment into our conservation and management approaches so that decisions are informed by this changing context. Now, before I go any further, let me introduce our speakers. Dr. Tommy Moore earned a PhD in oceanography from the University of Delaware with a focus on marine chemistry and climate change impacts on the marine environment. He's currently working as an oceanographer with the Northwest Indian Fisheries Commission, supporting the treaty tribes of Northwest Washington with challenges related to marine climate change and its impacts on fisheries, and other emerging issues such as offshore wind development and marine carbon dioxide removal. He has led and participated in studies looking at biological productivity in coastal waters, nutrient and carbon cycling, and small-scale variability on ocean acidification. Dr. Rishi Sharma received his master's and PhD in quantitative ecology and resource management from the University of Washington. He has led and participated in scientific teams at the national, regional, and international level, focusing on conservation biology issues such as threats to lamprey and ulican populations on the Columbia River due to climate change for the Columbia River Intertribal Fisheries Commission, to bilateral Chinook salmon issues, where he co-chaired the Chinook Technical Committee for a period in the aughts, to stock assessment of large pelagic species in the Atlantic Ocean, including yellowfin and bluefin tuna, and as the chief stock assessment scientist for the Indian Ocean Tuna Commission, where he led 20+ stock assessments and MSC development across tropical tuna. Rishi is currently a senior fisheries officer in the Food and Agricultural Organization, Fisheries and Aquaculture Division, where he's the lead technical officer for the Areas Beyond National Jurisdiction projects and the Ecosystem Approach to Fisheries Nansen projects. He's also leading the evaluation of the Global Stock Status Metric for FAO on sustainable fisheries. So for today's seminar, we're going to hear from Dr. Moore first, followed by Dr. Sharma. After the presentations have concluded, there will be a short break followed by a question and answer session moderated by Laurie Wykamp and Marissa Litz. Please use the question and answer feature in Zoom to pose your questions to the speakers. Everyone that's on this Zoom call can upvote the questions posed in the Q&A feature, and the moderators will choose the highest voting questions to pose to our speakers. If we receive more questions than can be answered in the time available, we'll endeavor to get written responses from our speakers and include those responses in a seminar package that's posted on the PSC site. Thanks, and now on with the presentations, beginning first with Dr. Moore.
Thanks, John, and I'll hopefully share my screen properly the first try. For full disclosure, I'm more of a chemical oceanographer than a fisheries scientist, so I will occasionally tread out of my comfort zone and talk about fish. Typically, even though I work for a fisheries organization, I try to let the experts talk on that, but more and more I've had to become more comfortable with that because working for a tribal organization, you get to wear many hats, and I should have put down other duties as described or as needed as my job title. But anyways, moving on. There we go. So just a quick overview. This is kind of I guess more of a framing question than an overview. But I just wanted to basically today I'm going to focus on the oceanography side of fisheries and some of the research that links it back to fisheries performance. And just as I guess something to keep in the back of your mind or front of your mind is for the different drivers or processes that we're typically think about on kind of a global or basin scale. There's El Nino Southern Oscillation, Pacific Decadal Oscillation, North Pacific Gyre Oscillation. These are all kind of basin scale processes. And more or less some can directly, indirectly, or sometimes not at all, depending on how the year's going, impact fisheries or salmon fisheries in particular. Regionally, marine heat waves, the timing of upwelling and intensity, food web dynamics, and then a lot of local impacts, especially for early marine survival, such as near shore sea surface temperature, productivity, oxygenamics. I should have put predation in there because that's also an important one. And then the other question to keep in mind is how is this information used in management? How could it be used in the future? I think some of this is actively used either by the technical folks, the policy folks, other stuff folks are aware of, but may not be applying. So, so moving on, I'm going to start at the very high scale. And for the most part, I'm going to focus on marine conditions, but I just wanted to highlight that 2023 to date is a fairly anomalous year, very exceptional. We've had September was the 4th month in a row for a record breaking global average temperatures. September was 1.44 degrees centigrade above the 20th century average. And if you look at the plot here at the bottom, this is from the climate.gov website, just showing the temperature anomaly or difference from average. And while they do put a linear fit to this data on there, I think they would have been better off doing a bit more of an exponential fit because the rate of warming is definitely, or at least to my eye, is increasing. And then so far this year, temperatures are well above average. If we look at more like global average sea surface temperature over time, this is a figure from climatereanalyzer.org based out of the University of Maine, and really great site to go to if you need general plots on climate. Unfortunately, they don't have anything that focuses on the Pacific Northwest, but they do have at least global plots. And in this one, the heavy black line at the top is 2023. The dashed line in the middle is the kind of the base period average, which they use as 1982 to 2011. And then the other two dashed lines are two standard deviations. And the yellow line is 2022 as a reference for how things looked last year. And so 2023 started out on par with 2022, much higher than the average and well beyond the standard deviations. But this is global temperatures are increasing, so you'd expect to, you wouldn't expect it to look like the average. But from April onward, temperatures globally have been anomalously warm, and we are moving into an El Nino, but typically that doesn't affect global temperatures until about this time of the year. Like over the summer, conditions were developing and would be felt off of the kind of coast of Central America, but not so much here or globally. But or so, global temperatures have got a head start on the El Nino. This is also evident in kind of monthly average sea surface temperature anomalies. So this one is using a 1971 to 2000 climate baseline. So similar to the previous one. I think it's actually the same as the previous one since it's from the same website. And again, global ocean temperatures have been increasing steadily, and the anomaly or difference from the mean have been steadily going up this year. In September of this year, we're close to like 0.7 degrees centigrade above the baseline. So still below the worries of, or below the worst of the, what's thought to be the worst of climate change impacts, but getting closer. And we'll have to wait to see like how things look in the future. Hopefully this is just an anomalous blip and not like a resetting. But if you do look at like the 2015-16 time period here at the right side of this figure, those were the time period of the last big El Nino. And for the Pacific Northwest, this is when the blob began. You do see that sea surface temperatures increased and have kind of plateaued. So my hope is this is more of a bump and not another stair step up. But we'll have to wait a few years to see where we're at. Getting to some of the basin scale drivers. First, I want to talk about specific decadal oscillation. This is a look at basically the kind of warm and cool versus cool period. This is driven by basin scale circulation upwelling, and during the warm period, conditions on the U.S. West Coast or the North American West Coast tend to be warmer. And in terms of salmon productivity, this tends to be a negative, tends to be low productivity, just not good conditions. We're currently have been in a very strong negative PDO for basically since the blob finished. And it isn't currently, it's not showing any signs of weakening. I don't know of any like forecasts for PDO to look ahead to see like, is this changing or not? You just kind of have to go by how conditions look month to month and go from there. But currently we're still strongly negative, which is a good thing for salmon. The kind of the new kid on the block is North Pacific gyre oscillation. This, as the name implies, looks at the gyre circulation in the North Pacific, or kind of the basin scale currents, and kind of how strong or weak they are. This will factor in and kind of include kind of wind-driven circulation and upwelling. And when the MPGO is negative, again, conditions on the North American West Coast tend to be cooler. You have stronger upwelling, and typically, circulation is stronger. So, more favorable conditions for salmon. And then what's been making the news over the summer and quite a bit over the last month or so is the I guess it's now officially an El Nino forecast to be a fairly strong El Nino through this winter. And what you can see here is, I probably should have shown a INSO neutral diagram to go with this, but typically in the Western Pacific, kind of north of New Zealand, Australia into Indonesia region, is a anomalously warm temperatures, and that drives the trade winds and circulation during El Nino. These conditions shift, and that warm pool, or basically the trade winds relax, the warm pool sloshes to the east, and this warm subtropical water kind of piles up on the coast of South America and will start to diverge and go kind of north and south. And presently, some of that subtropical water is probably moving up the coast of North America, but we're not really feeling that in the marine sense quite yet. But the climate pattern is very strong right now. And this is just a quick overview of the ensemble models that are looked at for this prediction. The solid gray line is the October, November, December forecast, which is kind of the next monthly period they would look at for forecasting. And we're currently well above the threshold, which I believe is 1 degree, where the Nino 3.4 anomaly is 1 degree above high. And all the models kind of agree we'll have a strong El Nino that will begin to weaken kind of next spring/summer. We'll say that the El Nino forecasts tend to be fairly terrible in the spring. And over the last 3 years, we had a three-peat La Nina, and every year the forecast was that we'd be going back towards neutral conditions. So the take home of this would be is we're probably going to have a strong El Nino through the winter, and we'll have to wait and see how it's going to look for next year. For impacts on the Pacific Northwest, or this is the U.S. as a whole, but honestly, focus on the Pacific Northwest. Typically during an El Nino, there's conditions will be warmer, and for the coastal regions, fairly average rainfall. This is opposed to a La Nina, where we typically would have cooler and wetter conditions in the kind of the Washington coast and up into British Columbia. However, these are basically, or sorry, the driver of this is a shift in the jet stream. This is another figure I stole from a climate.gov blog. And during El Nino, there's a weakening of the low pressure cell that normally sits up near Alaska weakens, and jet stream drops further to the south, and typically is then centered over the kind of southern U.S. During La Nina, you have the kind of the polar vortexes, as the weather services like to call them, trying to find new ways to make weather sound terrifying. And jet stream is stronger into the north and dipping down to pull more moisture up in the Pacific Northwest. However, these are kind of just statistical averages, I guess you'd call them. And shown here are the El Niños on record since 1957. So there's been 9 of them, not including this year's. And what we're seeing here is the differences in temperature. You can also get the differences in rainfall. But what I want to highlight here is that even though the forecast is for warmer and kind of average precipitation, that's not a guarantee. And on these, at least, 3 out of the 9, or 4 out of the 9 had average to cooler temperatures during El Nino. So really, it's a bit of a coin flip. Weather will be different, conditions will be different, but it's not like set in stone that that's how it's going to be. And coming back to the sea surface temperature anomaly, and this is now switching gears to how El Nino impacts the California current ecosystem, or kind of, by proxy, salmon fisheries on the west coast of North America. You do get these subtropical waters coming up the coast. They tend to be warm, and the kind of phytoplankton, zooplankton, and trained by them are different than what we normally have around. And prior to the blob, or to the kind of the most recent decade or so, this was a fairly good predictor of when you had warm conditions, you had poor salmon survival, poor productivity. And that's because the warm water was typically associated with an El Nino or these subtropical water masses. And that can be seen here. This is from the, the kind of website I turned off a bit off the bottom, but this is from the Integrated Ecosystem Assessment website that the NOAA puts together and gets presented to the Pacific Fisheries Management Council each spring. And what we're looking at here is the northern and southern copepod biomass anomalies. And the blue bars on these are the most recent 5 years. But what I want to call your attention to is the period before that, which would be kind of the 2015, 16, 17 period, which is the years of the blob and the last El Nino. And during that time, the northern copepod biomass was anomalously low, and the southern copepod biomass was high. And again, this was likely due to the El Nino being present, bringing the southern or the subtropical water masses further north, and thus altering what species are present. And why this is important for those of, I'm assuming everyone here but knows this, but just in case, is northern copepods are typically referred to as cheeseburgers. Southern copepods are referred to as celery, because northern copepods very high in lipid content, and very good for salmon to put on weight and rapidly as they enter the marine environment. Southern copepods not so much, so you wind up with kind of skinny salmon with low growth curves. The other kind of feature or new trend, and again, I keep referencing back to the blob because that time period has really, in my mind, signified a shift in how the ocean environment in the kind of north central and northeastern Pacific Ocean has been behaving, is presence of marine heat waves. Since the blob I think basically every summer there's been a large marine heat wave of kind of lesser or greater intensity. Shown here is the current conditions off of the West Coast North America. Blue dotted line outlines the US EEZ. And this marine heat wave has retreated quite a ways offshore. It's still present out in the central North Pacific and still quite warm. Over the summer, these waters reached right up to the coast of the US. And sorry, I thought I'd include a figure and I didn't. And we're reaching the coast of Washington, Oregon in particular, with some spots of warm water reaching California as well. Shown here, this is for this year, going from kind of May through the present day, is the total surface area of heat waves are the bars, and then colors are depicting percent of the US EEZ that was under a marine heat wave. And so kind of the marine heat wave reached the US West Coast kind of August, really started showing up in August and September, and dispersed moving into October. And that kind of corresponds with when the weather was changing and we're moving from the kind of summer upwelling season into more of a winter downwelling season. And this is a figure here, just looking at kind of over time. This is off that same website, and apologize that it came out a bit blurry. Thought I'd copied a bit or stolen a better figure. But this figure here only extends through 2022. It hasn't been updated for the current year. And what I want to call your attention to is the 2014, 15, 16 time period of the kind of the blob years again, because this has been a recurring worry of we have a strong marine heat wave this year and we're moving back into an El Nino. Are we going to see kind of the blob returning? And we can see there's the kind of for the blob years 2014, 15, 16 marine heat wave was very large. Temperature anomaly was quite high. And yeah, it was major. And then it was very long lived. Like it did not disperse in the winter. That was one of the major features, is this heat wave basically lasted for 3 years. Whereas most ones we're seeing now are kind of a summer phenomenon. And then with the winter storms, they disperse and then reform in the spring. And so a concern we've had is this a return of the blob? This is why I'm showing this figure is this is a figure showing the depth over time of the sea surface, or instead of sea surface temperature, this is just the temperature anomaly within the surface ocean. And one feature of the blob was this warm water mass reached down to roughly 300 meters. There's a pretty strong signal down at that depth. The warmest part of it was up the surface, but these water masses persisted at a fairly high depth. In the winter, storms tend to mix the surface ocean down to a depth of between like 100 and 300 meters. So when you have this warm water masses extending at great depth, the winter storms, unless they're quite strong, may not disperse them. And so that's part of what happened with the blob. The other part was it lined up with a positive North Pacific gyro oscillation, a positive PDO, and then a strong El Nino. So basin scale circulation was also weaker, which probably also led to this the persistence of the features. Not shown here, but for the current marine heat wave, I've kind of been tracking that through the summer. Depth of that has been between 30 and 50 meters, and after that, temperature tends to decline pretty rapidly down to the kind of seasonal depth. And looking at it, that's already happened. A lot of the seed has already dispersed. And so it's only this thin layer at the top that's currently present and was present throughout the year. So my hopefully not overly optimistic forecast is that, or prediction, I guess I wouldn't call it a forecast, it's just prediction, it's me waving my arms, is that we're not seeing a return of the blob. We are seeing these frequent annual marine heat waves affecting summer conditions, but they tend to push offshore and diminish throughout the winter. Looking a bit at local conditions, this is something I could ramble on at for the full allotment of my time, but I'll spare you. What I want to show here is just a snapshot of kind of what's currently been developing off of the Washington coast in particular. I know this extends down into Oregon, not so much up in the kind of Wanapukka Eddy, And conditions in the Salish Sea are a bit different because circulation patterns in there are more driven by flow through Strait of Georgia and riverine flow. But what we're looking at here is the Ocean Observing Initiative's mooring off of Cape Elizabeth. This one's at, I guess, 95 feet depth. That's roughly the depth of water this thing is deployed in. And on the left is kind of surface and bottom water oxygen shown from August and through October. And on the right is chlorophyll at the same time period. And so what we're looking at here on the left is that during the latter half of the summer, bottom water oxygen conditions were quite low, not as low as we've seen in recent years, but there was a strong periods of hypoxia, which is oxygen typically below, say, 1.8 or 2 milligrams per liter. And then this rapid increase in bottom water oxygen that coincides with kind of our first strong storm of the season, of the fall season. And then you see the low oxygen water mass reforming beginning of October and then dispersing again. And that's when we had our next kind of strong storm or atmospheric river pass through. And you can see this paralleled in the chlorophyll, where during kind of September during September, there's very high, very variable chlorophyll to surface. Some of this was observed at depth. This is kind of the phytoplankton dying and sinking. They still have chloroplasts, so they still show up as having chlorophyll at depth. And again, at the same time that kind of September 26th time period, where dissolved oxygen increased, you'll see that the chlorophyll numbers decreased. It's because again, strong storm, you'd have turning over the water column and kind of strong mixing that will disperse that productivity. And then chlorophyll again increased because largely there you'd have a big spike in nutrients from the storm, allowing kind of a fresh bloom to happen. Dissolved oxygen decreases at the same time. And then that next storm in October kind of reset things, and it hasn't really increased much since then. So that's kind of a typical end of the season. But I wanted to highlight this because it shows how variable conditions are off the coast. And the other reason is that for the Quinault Indian Nation, their biometrician had been looking at some of their salmon escapement or run sizes, and we're finding that there was a correlation with bottom water oxygen off the Cape Elizabeth area. Whether or not that's due to dissolved oxygen, I'm not sure, but it could also be due to the other kind of physical conditions that are driving this, like periods of stagnant water, poor mixing, or limited upwelling that might lead to this. So that's just kind of a preamble for one of my closing bits of we might need to look more closely at local conditions when forecasting and managing salmon, and kind of take a number of things on a run-by-run basis. All right, so I was quickly here just going to do a quick, just touch on a few publications on climate change impacts on the California current ecosystem and on salmon in general. This is a more recent one. This is focused mainly off the British Columbia continental margin. But just looking at this, they found that annual average warming up to greater than 1.6 degrees centigrade in the sea surface temperatures, increased stratification, decreased surface pH. So kind of what you expect and what most of the climate change forecasts have been showing. This is looking more near term though. So that's kind of where I'm focusing this on. And then from what they looked at, this is a model approach. And what they were finding is that stratification and increased wind speeds likely will have limited impact on nitrate availability. So nitrate just being a proxy for all nutrients for productivity, and for most parts of the ocean tends to be limiting. And the increasing temperature will lead to an increase in primary production. That's because most bacteria or zooplankton are strongly temperature dependent. And then this could have impacts on food availability for higher trophic levels and on the benthic habitat. Higher rotating to surface waters typically leads to lower oxygen in the benthic environment, because as these organisms die, they rain down to the bottom and start to decompose, very much like a compost pile. And this was just focused on climate change. It wasn't focused on fisheries impacts or fish species. So They didn't touch on the implications for salmon, where increased temperatures can lead to increased metabolic demand in the fish themselves, and or touch or anything of that sort. So this is just the change in the physical environment. This is a figure from Shui, 2018. Hope I said their name correctly. Out of Nature, and this is looking at a 20-year period from kind of spanning 1990 to 2009, and then in the near future, 2030 to 2049. And I kind of pulled this figure out because what we're looking at here is basically this is a modeled approach looking at the future using a downscaled model. And what they're predicting is that kind of stronger coastal winds are going to lead to increased upwelling. And that's why temperatures in the nearshore region are shown to be lower here by about, say 0.3 to 0.5 degrees C, or I guess only slightly warmer. Temperatures are thought to only be slightly warmer as compared to kind of the offshore water mass. But the bigger take home is on the bottom two panels, looking at kind of panel C, nitrate, and panel D for silicate. And this is showing a significant increase in upwell nutrients, which will then likely lead to increased primer productivity. So this could be a double-edged sword of increased surface productivity, could be better for salmon, could also lead to greater hypoxia and other kind of food web impacts. So it's, just having higher productivity doesn't always mean things are better, but something to keep in mind as a likely kind of trend over the next 20 years off of the West Coast. So do a couple of slides here of just kind of doing a fanboy for Lisa Crozier and some of her work of late. In 2019, there was a climate vulnerability assessment focused on salmon vulnerability. They looked at several ESA listed or Endangered Species Act listed salmon species on the West Coast. And in this, they considered sea surface temperature, ocean acidification, sea level rise. And for sea level rise, they're using that as a proxy for kind of impacts on the nearshore environment and estuaries, since those are the areas that be most heavily impacted by sea level rise. And then timing and intensity of upwelling and changes in ocean currents. Most stocks off of the Washington, Oregon region considered moderate to highly sensitive and highly exposed. Standard for doing a vulnerability assessment, you typically look at species sensitivity and exposure. And from that, then you can calculate a vulnerability. So just so that can put those terms in context. For the marine variables, exposure to ocean acidification and sea surface temperature were highest, with sea level kind of coming in second. But for ocean acidification, there's not a clear, the sensitivity was thought to be fairly low, although there's not enough information for knowing how ocean acidification will affect the marine food web, which could make that sensitivity a bit higher. That is something they note. But again, temperature is a big concern, and that's kind of why I spent so much time talking about marine heat waves. And then during this vulnerability assessment, there wasn't a clear cut like which life stage of a given salmon species was the most vulnerable. So for some, it's the juvenile or the early stages in the freshwater. Others, it's your early marine survival, or for some, it's can you come home and successfully spawn. In 2021, Lisa get a second paper on looking at climate change in the Chinook life cycle. This is looking full life cycle vulnerability assessment or full life cycle model for select Columbia River Chinook stocks, looking at a kind of a range of future climate scenarios, mainly the 4.8 and 8.5, which is kind of the moderate and kind of business as usual high emissions scenarios. The major take home from this that I found is that negative effects from increasing sea surface temperature drove most of those populations to an extinction threshold by the end of the century, and impacted the marine stage, reduced survival in the marine environment by kind of up to 90%. they do say that they do put some pretty strong caveats that, the North Pacific might not warm at the model rate. And again, that kind of comes back to, figure here where coastal warming might be lower than the kind of North Pacific average. And then there's also potential for kind of ecological surprises, because it'll impact both bottom up and top down trophic processes. So while the fish might be more stressed, if there's an increase in productivity, there might be more food available. So therefore survival could stay the same or go up. So kind of a big unknown there, and something to keep in mind over the next kind of 10 to 20 years. And this one I threw up, and I'll leave my slide deck, but I'm not going to touch on it here. This is a very in-depth literature review released this year. I think they reviewed kind of, I think, 1,000 fisheries papers and 1,500 marine kind of physical oceanography, chemical oceanography papers related to climate change. The driver note I just want to take home from this one is they do, or at least it does highlight kind of carryover from the freshwater life stage could be of concern, or is carryover from different life stages. If you're unhealthy going from juvenile to adult, you're probably unhealthy in the adult stage or have lower survival. So adding more complication to how you look at environmental impacts on salmon. The different life stages aren't nice, clean cut little boxes. And this one I went through because it's a publication I've been waiting for probably 4 years for. Finally came out. It was becoming a bit of a running joke, and or not running joke, but kind of a bit of running notoriety, and at least the ecosystem working group at the Pacific Fisheries Management Council, because it had been so long in coming out. But this paper looks at sensitivity of kind of federally managed stocks along the U.S. West Coast. And again, looking at the sensitivity and exposure to determine vulnerability. For salmon stocks, they all ranked kind of high or very high in the case of Chinook in terms of vulnerability to climate change. And this one, they only looked at a handful of drivers. And showing here their summary table for coho salmon is just gives you an idea of the different drivers that we look at. They do have sensitivity to temperature, sensitivity to ocean acidification, both which are fairly low. And then exposure, so exposure to ocean acidification would be high. Exposure to marine surface temperature, moderate to high. And from this was done by, ranked by a group of kind of expert scientists that work through this. And what you have here is a mean score and a data quality. Basically, data quality is looking at, was there good scientific evidence for these impacts, or is this more based off of expert opinion? So higher the score, the more evidence there is. And so some of these, like if they're down at a 1, that was just based off of expert opinion. There hasn't been a study that could link this either way. But again, I want to highlight this because it shows a number of variables we should be looking at, but it also shows kind of the limitation of what's currently being looked at or what we understand, because it's not really a driver in here, or there's no sensitive exposure to things like to anything in the food web. I guess there's a prey specificity, but that's is the fish a generalist, or do they eat only certain things? So ideally there'd be like a northern copepod, southern copepod, or something of that sort driver. So a lot of room to work for here, but it does mean in terms of climate change for salmon, we do need to keep a close eye on climate variables. And just highlighting another project here. This is one that has recently wrapped up, the Salish Sea Marine Survival Project. And I encourage you to go look at the link on this if you haven't, or if you weren't involved in it. They identified 2 overarching phenomena behind declining marine survival in Salish Sea. One's a change in the food supply, likely driven by changing environmental conditions, nutrient availability, and temperature. Again, these aren't fully understood, but that's kind of where the evidence is pointing. They also note declining forage fish populations, which could be due to things like, again, it could be driven by climate change, possibly due to marine pollution issues or loss of nearshore habitat. And then increase in predators. This isn't a climate change driver. This is a a management success driver in that we've been successful in recovering marine mammals and have an increase in seal and sea lion populations. And due to alterations in the nearshore environment, we've created, in some areas, we create kind of predation hotspots. In the Salish Sea area, this can be the Hood Canal Bridge, where kind of fish kind of pile up behind the bridge and are easier for predators to get at them. Other spots can be alterations, like creations of docks or other structures that fish will use for shelter, but also attract predators. And another thing they flag is the consolidated timing of hatchery releases. If you release all your hatchery fish at once, you have a large pulse of juvenile fish entering the marine system. And that's a lot more appealing to a predator than a gradual trickle of fish out of the marine system. Just bear in mind. Another project I want to highlight, and I think is kind of touches on one of my recommendations I'll give at the end, is this work on early marine survival by Tulalip tribe. It's kind of driven by Mike Crewsome. And shown here on the left is a figure modified from Duffy and Beaucamp in 2011. And what they're doing in the study is looking at kind of hatchery salmon size and length at age. And they're also doing zooplankton toes at the same time. And this is based off of, basically they're trying to continue this work that's done by Duffy and Beaucamp of looking at this critical growth period in kind of June and July, when there's a lot more zooplankton available and growth rates were much higher, versus September where growth rates were much lower. And you wind up with a kind of much larger, faster growing fish with a higher survival rate. And on the right here is just a map of their sample sites. Purple sites are areas where they did both Persane and zooplankton toes, and the blue sites are just zooplankton. This is work they're working on getting more funding to carry on, but something that's been largely a grassroots initiative led by them. And full disclosure, I have written letters of support for this and do encourage more work of this sort. Moving a bit out of my comfort zone, this is something that I did review as part of the scientific and statistical committee for the PFMC. This is kind of an update to the Oregon Productivity Index hatchery forecast, OPIH area. This is the look at the forecast of hatchery and natural returns for coho in the kind of Oregon region. And prior to, say 10 years ago, prior to the blob, the OPI model was very high performing, did a quite a good job of predicting salmon return or forecasting salmon returns. And it primarily looked at jack returns and smolt release timings. And then over the most recent years, the model's been consistently kind of over predicting returns, especially on low return years, which is very concerning because this complex is a very large contingent of the coho catch off of at least the kind of Oregon-Washington coast. And if it's over forecast, it'll lead to kind of overfishing on smaller runs off of especially Washington coast. And so this new model is looking at, it still uses jack returns and smolt releases, but it's also considering 9 different environmental variables in a REMA model, which is a kind of a fancy moving average type model. And they're kind of using kind of a kitchen sink approach, throwing everything at it. The model evaluates different combinations of 0 to 6 of the environmental variables. And then we use an ensemble of the top 10 fits to the data to predict a model for a given year, and then they'll project that forward for what they anticipate for the next year. And this has, for the most recent 10 years or so, this is a significant improvement. This is still under development. It's was reviewed during this year's salmon methodology review and is going before council in November. For further discussion there, and there's still more recommendations coming out, but I do think it's an interesting first step. And since 2014, the major, I guess, variables that have matched up well have been jack returns, North Pacific gyro oscillation, and Pacific decadal oscillation, all lagged by 1 year. winter sea surface temperature, and the fall El Nino index. And the reason I include this here is I think this is something that could be used elsewhere, not necessarily for forecasting. I'm not brave enough to advocate for changing forecast approaches, but I think that using this type of approach might be a way to identify what are key variables that are driving um, a given salmon stock returns. And once you identify those variables, you can start working on a more mechanistic approach rather than kind of this brute force approach used here. And something that hopefully I'll have time this winter to dig into and explore it further. So wrapping up, kind of what can be done. We already have stock light charts. This is a good first step and has gotten folks in the salmon world very familiar with looking at trends and incorporating ecosystem data and at least into their thought processes. Greater incorporation of environmental variables into forecasting. There's some challenges here of increasing uncertainty and variability. Trends that are relationships that existed in the past don't necessarily work now. Increased understanding of vulnerability at all life stages, including carryover effects. This is something that is challenging, but I think is very important to understand this full life cycle of the salmon and how these effects can be additive throughout. And then as an oceanographer, my personal bias, better understanding of marine survival. I think this should be prioritized more when we discuss salmon recovery. If we can boost marine survival by a small amount, that's quite a few more fish that are returning home at the end of their life. And with that, I'll wrap up and start rambling at you.
Thanks, Tommy. Our second speaker today is, as John said, is Rishi. And Rishi, I'm pretty sure you're there. So if you want to take the floor and share your screen, we'll keep going.
Good afternoon, everyone. It's kind of late
So
here.
we see it in the full view, not slideshow. There you go. Perfect.
You're in slideshow. Okay. I'm going to try and keep this really focused because we don't have a lot of time here. So I'm not going to go over a lot of case studies, but I'll let you all look at that at your own time. There are two reports that I will be drawing from, which I can just briefly give you an overview on. One was taken out in 2018, and it's on one was taken out in 2018, and it's basically dealing with impacts of climate change on fisheries and aquaculture, synthesis of current knowledge. Numerous authors are part of this effort, and it's basically giving an overview of how adaptation, mitigation could work within the context of climate change and fisheries. And another one that was taken out a couple of years ago is adaptive management of fisheries in response to climate change, with a bunch of case studies. I'm going to be covering one of the papers in this second approach that I led as an author with 4 other colleagues, and it's going to talk about really what kind of fishery management structures do you have in your toolbox really to mitigate for what you might detect in a system that's changing. And we go back to the beginning of the talk. Basically within the context of reference points, and then when do you detect a signal, and then what do you do with respect to. So there are typically 2 issues that we deal with in marine fishes, and one of them is changes in species abundance, so community composition, namely food availability, larval transport, temperature of predators, things that Tommy gave us a good overview about. And the second is changes in spatial distribution that happens with these stocks. And so the abundance could be affected, spatial distribution could be affected, but how does this really affect the bottom line of management and how do we do business? That's kind of the key here. So I will give you a quick overview of objectives here and some resolutions that have been put into place in tuna FMOs in particular with respect to achieving some certain objectives with certain probabilities, reference points, and how that really works within the current management approach, and alternatively rethinking what we are managing for. Finally, we'll present you a framework on how we quantify risks based on current understanding of the system dynamics, and presenting sort of an MSC framework, case studies to address these changes and to assure that you meet certain objectives with a certain probability. So a lot of you might be familiar with this, may not be familiar with this, but in a lot of the tuna world, and also in a lot of the world in the sea, and a lot of the world in Canada, is using some sort of approach which is similar to this, which basically you have 4 quadrants. On the x-axis you have basically your MSY, BMSY target, and you scale your current biomass with respect to that. So it's between 0 and 1 is here, and then something greater than 1 if you're scaling it all to that. And similarly with the fishing mortality, you have a target fishing mortality, and everything is scaled relative to that. And you're trying to keep your stock hopefully in a region where you're exceeding your BMSY target, the point at which you maximize your yield, and hopefully you're not putting too much fishing pressure on it, so you're less than that. Ideally, if you're fishing at FMSY, and you should be close to basically the intersection of this where your stock trajectory is. And if you are in this quadrant, you have criteria like this, probability that you will reduce your fishing mortality to a point which is less than FMSY with a high probability and a short period. These are all quite vague terms that have been put in sort of resolutions and management. They're called CMMs, which are basically management and compliance sort of mechanisms by which RFMOs operate in the global world. And then if you're in this quadrant, you want to achieve a certain target with a short period by reducing your fishing mortality. And if you're in this quadrant, you want to rebuild the stock in a short period so that you need from here. So the idea is that your stock should be healthy, and how quickly can you bring it back. And you do that with something like a reference point based system where you operate with a certain target fishing mortality with a buffer around it, and you try to achieve these targets as with some definitions that you have to use. So high probability, IPCC uses 80%, Government of Canada uses 75%, Marine Stewardship Council uses 70 to 80%. A short period for recovery purposes, the US uses 10 years and 1.5 generations. Australia uses something like 10 years and a generation. Marine Stewardship Council uses 2 generations. What kind of targets you would try to optimize this? It could be some fraction of FMSY, And where do you take a management action is when we call it a threshold, this point here. And where do you stop fishing completely? That's at some point where the biomass achieves a value here, which in some cases is 40% of BMSY, it could be 20% of BMSY. And the threshold is basically when you start implementing sort of controls on your fishing mortality levels, either through effort or tact limitations. So these are all based on MSY targets or proxies, and implicit in all this is an assumption on your achievable harvest and process error in the system. But how does this really change with climate? It's an idea that Dave Bernard had sort of taken out maybe 15, 20 years ago now, and with the Chinook Tech Committee. And he proposed that either the spawning biomass, when you see something in a system, your biomass is either being low for a few years, and why would that happen? Either it could be due to a passing weakness in year class strengths, and there shouldn't be any action taken, or is this a start of overfishing and additional action is warranted? And so the idea here, again, it's very simple. You have a cumulative distribution curve that would be achieved with some sort of achievable harvest rate. So whatever system you're operating on, you will achieve a certain cumulative distribution of achieving a certain target with that regime and the process error within that system. However, the system changes, this distribution will change. And so when it changes, that's when you have to really, do you detect that change and what's your response to it? And the objective really here, maybe you want to have a probability that the spawning biomass level is kept above this target with a 90% certainty. Now, in order to do that with this new distribution function, you would have to really drop your harvest rate significantly to do that. Because even when this happens, you'll have, and you'll keep fishing at a certain rate, you would, in this scenario, you would achieve that target only like 30% of the time, and that would be an indication that something's happened in your system and you need to do something about it. So I'm going to give you a quick example of this, and it's not important about, you know, in sort of, we always think as biologists, what's the mechanism and how is this going to happen? And I'll show you the different mechanisms that could possibly give you a signal like this, a very simple simulation. And so we took an age-structured sort of model for Atlantic tuna stock, North Atlantic tuna. And we took different parameters on how it behaves. It has a life cycle up to 10 years. There's survival at age, there's a vulnerability at age on the fishery, there's a weight at age and a maturation at age on the stock. This fishery is quite complex. There are 12 different fisheries in this stock with different gear types and different selectivities. And so for purposes of this, we are not trying to model exact system per se, but we're trying to make some inferences on what would happen on this. And so we looked at a sort of a composite selectivity from the multi-field model, and what we use is this blue line, a selectivity for the stock. And when we do that, and we have some process error in a system with some variation, we can actually estimate through that sort of a dynamic yield production function where your fishing mortality should be and what your targeted yield should be on the system. Simple, you know, yield per recruit type stuff, but you're really taking it up to scaling it to the population level with the R0 as you're using a dynamic yield production function, really. So, and you can simulate them based on different sort of mechanisms in your population having either, autocave correlation, which is negligible. So there's no time series effects on recruitment, or there is a very strong time series effect on recruitment, and you'd see different signals on how the population varies over time and what the corresponding harvest might be over time. And based on those scenarios of autocorrelation, either no autocorrelation or more autocorrelation, you can't really see the changes, but these cumulative distribution functions change the spawning biomass level and how it responds to this and the different assumptions changes. So, and that's important because that's how you're going to detect a signal or not. And so under sort of baseline conditions, without any system perturbations happening, you would have a distribution function that looks like this. Now, if productivity drops by 50% in this population, the distribution function will change and it'll be something like this. And if the carrying capacity in R0 drops on this population by 33%, it'll go even further to the left, and if both the capacity and productivity on these system changes, it'll go even further to the left. So all these are showing essentially the likelihood of going below a certain level when you used to assume that the population was here, and you start detecting population going to 60,000 spawners, like 10% of the time, when you would barely ever see it go in the cause before. It tells you that something's happened to the system and you have to change what you're doing in the fishery. And the reasons for that are pretty obvious. So this is your baseline production function based on the assessment that was done in 2016. But if any of these other scenarios happen, you would have a different production function, really, and which would mean a different target reference point and a different way that you should be fishing. So if you're fishing, assuming this condition, you're going to achieve a bad situation on your stock more often because you're over-optimistic in how the system is behaving. So that's just with recruitment changes or changes in productivity. So if growth changes because of availability of food or predator-prey abundances or changes in things like that, you get a very similar effect again. It shifts to the left, and then your production function again changes. If selectivity changes in a fleet because of the overall selectivity, either now chooses for whatever reason the albacore are now further deeper, and you're fishing at a depth which is in the right depth, then they're less vulnerable to the gear. It'll have a positive effect. If they're more vulnerable to the gear and become more closer to the surface, it'll again have. So the yield curve is a function of the selectivity, obviously, and again you have a response which is similar to what I showed you with the recruitment dynamics. So if they become less vulnerable to the gear, it moves to the right. If it becomes more vulnerable to the gear, it moves to the left. So very simple model, but it tells you really sort of, and you could do this very simply with your salmon models, your age structure models, and Chinook and Stockad, or whatever you're looking at. It'll show you the similar sort of dynamics, and you can see what is your response going to be if you see this. If you see an event that was supposed to only happen 10% of the time, and you're seeing it 20% of the time, you don't really care whether it's mechanistically happening, because selectivity has changed or growth has changed. both have changed, or productivity is the problem. Your response on the fishing management sort of interval is to do something about that. So as soon as you detect something like this, what's your response going to be? This is something that was taken from CCSBT process, and essentially what you have here are sort of your management objectives, which are social, economical, political, and that defines really a lot of how you achieve these objectives with where your reference points are. And then on the system, you want to define really where you don't want to go. You want to define where your target is, and what are the biological constraints defining limits on it. Within the adaptive management cycle, you have a stock assessment, which you all do, where you think we are. You have some performance indicators of how we are doing with relative to these targets. And then based on that, you want to modify the way that you really fish. But predefining these rules of operations is key. Otherwise, you'll always get into the argumentative cycle of how much do you want to change and how much of a cut do you do. And so having this predefined is key to have all this working properly. And you've done this again with some species on the West Coast. So I'm looking only at the West Coast sort of case studies here. One I will bring from Australia, but Oregon Coast cohort. You've seen the abundances go up and down quite a lot. It was listed back in the 90s, and since then the harvest has really dropped a lot, and we haven't really seen things bounce back as much. But again, implicit in this, there's a control rule in how you're supposed to fish, and there are lorries there, and I'm guessing Robin's around too, and so they can explain to you really what the target thresholds are with the different levels of abundance, and how you really operate your fishery based on those rules depends on the abundance level and your allowable fishing mortality at those levels. And basically an FMT guideline was developed, established sort of recovery plan and how it was supposed to operate within the context of the overall abundance and forecast mechanisms. And within that framework, you had 4 units, but you would have a realized exploitation rate between 10 and 35%, depending on the levels of abundance that you saw in the 4 different units, which are aggregate units on the coastal. And this has been fairly successful, though the stock hasn't really recovered as yet. So, and there was modifications to this. So, and that's the feedback mechanism that you have within your operation of how you're operating your fishery, you're operating how you do. Going back to that figure that I had here. So you define the management action, and then you can have an adaptive management cycle by which you can really change some of these. So you can modify and amend your rule by which you operate on these fisheries. I'm going to really go into that in much detail, but I think this was the new rule that was amended, and there were different steps and different rates at which you were operating, depending on which group you were in different areas that you were, and what kind of spawning abundance you were, whether you were critical, whether you were low, whether you were medium, whether you were high. You would basically operate at different levels. Another case study in the West Coast is the sardine, Pacific sardine. This is material borrowed from one Zelensky and David Gemma in the NOAA lab. And here you can see that Pacific sardine are difficult to predict. Is there a relationship? Maybe, maybe not. Definitely not. Maybe there is. So it keeps varying depending on the year and how many years of data you have and what kind of production function you use, and whether you actually can estimate the shape of either recurve or divergent production. But the point is that doing this post-hack talk, always you find something that might fit, and you can take into account environment and recruitment variation with this. It can vary, like steepness is sort of parameter telling your productivity of the stock, so it varied from 0.36 to 0.8, depending on the year that you were using in your assessment. And why was this so much variation? It was all driven by process error and essentially by the environment. So the environment is really key in this talk. It's being shown that things like sea surface temperature have really positive correlation with this, and surplus production increases in increasing temperature. So the exploitation rate implicitly could be based on a temperature measurement which they were using in your area. And this system worked quite a lot, and so the rule really was a function of the distribution of the stock which they were getting to Telcofi surveys, fraction that was vulnerable, and then basically estimated and what the threshold biomass level would be, and then this was the amount that you would be allowed to catch. But this fraction was bounded between 5% and 15%, and this would determine your overall quota. And this is where the stock recruitment functions feed into the biomass estimation. So you can see basically, there's some sort of a time series effect on recruitment, or there's a big decline on the stock. But it's really modulated by the environment. The Telcofi sea surface temperature did not inform starting recruitment, and the southern stock, northern stock overage, how they're actually mapping might have some influences with temperature and recruitment, but there's also an effect of TDO that affects recruitment. But in essence, a signal from the climate and temperature really has a very strong relationship with the biomass available on the stock over time. And that's really what they modified the relationship here a bit with a new temperature measurement, which was a function of the survey measurement as well as the Scripps peer measurement, and that's now used as a predictive measure. I'm not showing that here. So another case study, it's a more sort of a data limited approach. We don't have that much data as we had in Saudi, school, for example, but even Forgiani from CSIRO is leading this work, and really what they're trying to do, this is a banana prune, and they're trying to relate in Australia, this is the area that the fishery does, related to sort of rainfall. And again, this is the standard Beverton Holt model, but the process error is the residual is a function of Q1 rainfall deviations. So, and the predictive capability is pretty good. And so you don't really have a whole amount of data here other than catch and what your expected BMSY is for this population and how you're operating with it over the last 25 years. Right. Surface temperature is another indicator possibly on this, and you can see there's an anomaly here. There is also an anomaly with your La Nina and El Nino oscillation. So the values of Southern Oscillation Index above +7 typically indicate La Nina, while sustained negative values below -7 indicate an El Nino, and values between +7 and -7, this area don't really give you much variation. They're neutral conditions in recruitment. But when you get into these anomalies, they have a big effect on recruitment. And you can look here at a very simplistic way, really, this negative Southern Oscillation Index, the positive Southern Oscillation Index, and your average catch per unit effort, how it varies over time. And it's highest when you have positive Southern Oscillation Index. It's neutral in this range that we said, and it's really low when you have the negative Oscillation Index. And so you can come up with something like a simple control rule that if you've got high CPUE, high rainfall, positive Southern Oscillation Index, and neutral condition here, and if you have low CPUE and a low negative Southern Oscillation Index, how would you fish based on this just simple indicators? You could decide and develop a mechanism of how you should operate your fishery based on external indicators as rainfall and CPUE, rainfall and Southern Oscillation Index as to how you might want to fish. So understanding and predicting interannual variability in recruitment and catches, it's useful for predicting bad years. But this was a multi-species fishery, so it also depends on performance relative to fishing other species. So was that a spurious effect of this low CPUE because you're fishing on something else? So you really have to understand your data within the context of your fishery and how to use it. And you could revise, you could develop a harvest strategy really to include both the economic and environmental conditions. And I think the paper seeing that this was a couple of years ago. Some conclusions really. Management strategy evaluation is sort of a tool which is used extensively in fisheries now, and it works well with climate change and climate scenarios. So one of the things that we always use standard reference points are dynamic. That's system changes, a lot of these change. And so what do you do when you have these changes in a system? You have to change the way you develop your fishing mechanisms in it. So using the precautionary principle is key. We need to have the right sort of measurements and monitoring and evaluation tools to assess these changes with routine examination. So you detect a change in the system. What do? You have an indicator. Based on that indicator, you decide how you fish or you don't fish. And it's not all bad, as I showed you. Sometimes the selectivity change can have a positive effect, and it's not always negative in a perspective that we've tended to focus on in salmon. So a lot of ideas were taken from different people, and a lot of people have helped worked within the past on this. Dave Bernard, John Walter, Roman, and Greg Foster. Like Yanni ICAT, the Kaplan Center for Population Modeling. A lot of instrumental in a lot of these ideas. What we think may be a possible future way to manage these fisheries, per se. As I said, there's more information on a lot of this, the two reports, with, especially this one, adaptive management of fisheries in response to climate change. They are multiple case studies, which, you know, I can give you a quick overview of here, but we don't have that much time. So there's basically 14 case studies here. Um,
Why don't we?
You can open it up to questions because there's not much time there. But essentially, you know, they're from data limited fisheries to pretty data intensive fisheries in Philippines, Myanmar, South America, the US.
Great. Those look like it looks like a really interesting reading to see what other people have been doing. Why don't we move to the question part, Q&A, and our first question is for Rishi. Rishi, Gary Morishima says the figures on spawning biomass under changes in productivity seem to indicate a need to reduce exploitation rates under steady state conditions. Any guidance on how much to reduce ERs and when in the face of uncertainty?
So, I mean, one, you'd use the precautionary principle, you know, in effect, and a lot of it would depend on the parameterization you have of the stock complex or stock you're looking at. So, if you've got a whole range of, you know, alphas and betas from the population at large, and you may want to decide to work at an exploitation rate of the alpha and beta combination, which is the lowest resiliency in the population, and then build a buffer on top of that as well, because, you know, the systems change per se, so recruitments drop, so your alpha parameters actually drop. So I'd say, you know, reduce it to begin with, you know, somewhere like 50% of what the optimal rate would be there. Have some feedback on it, and maybe you could increase it in the future if you get better information and more data to really parameterize that function, you know, where you should be at in the new state. So.
Thanks, Rishi. So I have a question also for Tommy. So Tommy, you had mentioned one of the important considerations is local variability in the region. And so could you just speak very briefly about sort of the life stages that are most effective at, you know, is it out migrating smolts? Is it returning adults? So how do those local environmental effects affect salmon?
Yeah, thank you. I guess mostly it'd be on the out migrating smolts on that kind of critical stage when they're first entering the saltwater and working on rapid growth and survival. I think for returning salmon, there probably are some local effects because like this year we had fairly strong drought along most of the outer coast, and talking with some of the fishermen here, before the fish even started returning up the rivers, and they were already beat up and turning red because the rivers were so low that they had just been piled up in some of these pools waiting to go upstream. Were somewhat fresh, but there wasn't enough water to get up their spawning grounds. But mainly it'd be the out migrating smolts.
Just notice that. One last question before we call it a day. Rishi, harvest control rules assume that changes in fishing pressure will determine increases or declines in abundance. For some salmon stocks or species, productivity is the main factor that is currently determining trends in abundance, with fishing mortality being a minor contributor. How do we deal with the decline in the effectiveness of fishery management measures under climate change when F is going down? Yeah.
What you're saying is that basically your production function by which you are setting your F is is continuously declining. So to the point at which, you know, your F would be probably 0, and it's all driven by process error and variation. I don't know if it's directional or it's bidirectional, because if it's bidirectional, then you could have huge recruitments to massive runs. If it's unidirectional, then your only response really is to close your fishery. So the question is, when you really have a lot of variation in these systems and they go up and down a factor of 10-fold or 15-fold, the sardine example is key there. If you can find some signal that really relates well to that, and then set your management sort of system with that signal, then I think you could have something that works. But it's really difficult otherwise. It's practically impossible, I think so.
Thanks, Rishi. We are now ending. We want to thank both our speakers today, Tommy and Rishi, for a really interesting seminar. Our next seminar is going to be Wednesday, November 29th, and we have a discussion on hatchery production and attitudes towards hatchery production, particularly in the Columbia River, with Bob Lackey and Jason Wong, tentatively. So stay tuned and come back for that. And thank you, both our speakers again.